use some examples in a minute. Okay, but bear with it. It's actually quite it is quite interesting. So we're going to be using this callback libel thing again, and we're going to use this to try to make a kind of simple algorithm to optimize this marginal likelihood that we've summed over any latent or missing variables. So the key idea is that this EM is going to enable us, at least at some stage of the algorithm, to actually decouple the parameters. So I mentioned before that the problem with the missing stuff or the latent variables is that the summation of the latent variables actually couples the parameters together in a kind of nasty way. And the idea a little bit is that the EM will kind of help us to actually not have that coupling. Kind of at some stage of the algorithm, it will decouple the parameters like we had before. Okay, so bear with it, and we'll get there. So the way it's going to work, it seems very obtuse, but we're going to consider what we can call a variational distribution Q on the latent variables given the observations. So it's going to be called Q of H given V. Okay. What is it? Well, I'll tell you about that later. And we're going to consider the KL divergence between this Q on the hidden variables given the visible variables and P on the hidden variables given the visible variables are theta. So remember the object of this game is to maximize the probability of V given theta, the log likelihood of the observed data given theta. Maximize that. So the KL divergence is the average of log Q minus the average of log P with respect to P. Sorry, it's Q in this case. So the average of log Q minus the average of log P. Okay, and we know the KL divergence is greater than 0. We proved that. So using Bayes' rule, EH given V is joint distribution of V, you can plug this into here, and we're going to end up with this sort of entropy term here, Q log Q term. We're going to get here, we're going to get a minus P of H comma V, and then a minus log PV given theta term from Bayes' rule. But there's a minus minus, so it's a plus. So then we've got a plus log PV given theta on the left. So we can then put everything else on the right. So we end up with the log PV given theta is bigger than or equal to this minus the average of log Q plus the average of the joint distribution H comma V. Okay. So this is interesting. So what we've managed to do is this is the quantity that we are wanting to maximize. Log PV given theta, or we may as well maximize equivalently the log PV given theta. So it's bounded by this term here, which is the entropy of the Q distribution, plus this expectation of the log of the joint with respect to Q. And this bound holds for any Q distribution. So any Q you like, then I'll get a bound. And we have equality when I set QH given V to be equal to P of H given. Otherwise it's a lower bound. Okay, so this may look a little bit pointless, but the interesting observation about this is that we have here the joint distribution over H of V, and that's going to be very convenient in many cases, actually. When we've got some kind of structured distribution like a belief network, then the structure is going to appear here in its joint form, and when we take the log, this will sort of break the distribution into sort of its constituent parts, and that will make life a little bit easier. So this is kind of the key observation there. Okay, so what we're going to be doing is the following general idea. Rather than maximizing this directly, we're going to try to push up this lower bound. So we know that the log likelihood with respect to theta is kind of up here. We know that this lower bound on this function, so it's beneath it. So rather than pushing up the log likelihood itself, we'll do some optimization algorithm for that. We're going to try to push up this lower bound. And by pushing up this lower bound, we're hoping that this is not going to be a bad thing, that actually the likelihood itself will at least not go down. Okay, so that's kind of it's a surrogate objective. We're pushing up the lower bound rather than the objective itself. And in fact, we will show that for some special case, in fact, we can push up the likelihood itself, not just the lower bound by this procedure, but in other words, pushing up the lower bound actually is equivalent to pushing up the likelihood. So historically, these terms are called the entropy and the energy term, and this is a kind of a nomenclature that comes from the physics community, because this bound was very well known by Boltzmann already in the 1870s. It's a very, very old idea. The statisticians, they call it something else. They call it they call this the entropy. They call this the expected completed log likelihood, something like that. But that's a bit of a mouthful for me, so I'll call it the energy. And they have their own way of thinking about this, which I don't like so much, but this is a more general approach, and we call this in machine learning, we call this variational EM. So this is going to be the following. We're going to first of all do a two-stage procedure. Someone is going to give you these Q distributions, QH given B. Maybe they're just random distributions, okay? And then they're going to be fixed. And then they're going to say, well, okay, I'm going to now optimize this bound with respect to theta for fixed Q. Okay, so you then concentrate on this energy term, because this is fixed, and you maximize this now with respect to theta. And my point is that this will be a little bit more convenient often than otherwise, because we've got the joint distribution rather than marginal here. Then, given theta, we're going to say, well, what's the best Q? So we're going to consider a family of Q distributions. And within the family of Q distributions, you'll find the best one, the best Q distribution, which maximizes this right-hand side, which is equivalent to minimizing the k other divergence between Q, HKB, and P, HK. Within whatever family of distributions Q we are examining. Okay, so then I'll get a new Q distribution, a set of Q distributions. Then given Q, that new one, I'll then try to find a new theta. Okay? And I'll keep iterating this process. So it's a kind of coordinate-wise optimization process where we've got two sets of variables. We've got the Q's and we've got the thetas. We'll fix one and then optimize with respect to the other and iterate. Okay, so let's look at how this is going to work in a little bit more detail. So for IID data, that means the log likelihood is going to be the sum of the log likelihoods of each individual data point. So the log likelihood of the whole data set from some visible variables B1 through to Bn is going to be, each of those is going to have its corresponding lower bound. We can sum up the lower bounds and we're going to get this. So for each, it's exactly as I said before, but now we've got one of these entropes and energies per data point. So we're going to need a Q per data point. Okay, so this is the procedure. So the E step is the expectation step. Is we fix theta, we figure out what are the optimal distributions of Q from whatever family we wish to search through. And then the M step, the maximization step, is given the Q's, we find the best theta parameter by maximizing the energy and the expected complete log likelihood. The classical EM, this is the expectation maximization algorithm, the EM algorithm, is exactly this, except there's a very special setting of this Q distribution. They choose the fully optimal one. So for a fixed theta, the fully optimal Q is just equal to P. Conditional pH given B. You know that because the whole bound came from considering the minimization between these distributions. So it's clear that the optimal distribution is given by this set of P over all possible Qs. So what does that mean? It would mean, say, you could start with, say, some theta at time, say 1. Maybe you just make a kind of guess. then you, for the EM algorithm, with this optimal setting of Q, what would it mean? Well, you need to maximize now, the M step would maximize the energy, okay, with respect to theta. The energy is the expectation of log PH comma V given theta with respect to your Q distribution. Your Q distribution, the EM is the P distribution, which is P of H given V at theta 1, your current setting of theta. And this is some function of theta. You maximize this. So theta 2 is the max of this E of theta with respect to theta, so the argmax. That theta which maximizes this function. This gives you a theta 2, and then you go back and say, well, now I've got theta 2, I'll look at the energy now of this thing here with theta 2 here, and that'll give me that theta 3. That's the EM algorithm, where each stage you're using the optimal Q. So let's look at an example. So I apologize, this is a continuous example, so there's going to be Gaussian and stuff here, but it's not really a big deal. I wanted to make something reasonably simple. So we're going to try to look at a problem where we've got there's a discrete latent state problem. So we've got P of V given H and a P of H. And P of V given H term is a Gaussian distribution. Okay, so it's going to be a Gaussian whose mean is affected by H. So H is either state 1 or 2. So theta essentially is going to correspond to the part of it's a parameterization for the mean. So if H is 1, the mean will be theta. If H is 2, the mean will be 2 theta. Gaussian distribution. So it's a one-dimensional thing, and sigma squared is some known, I'm going to fix it, some variance of this Gaussian. Okay. And I'm going to set the distribution pH to be uniform. So if let's imagine that pH is 1, 2 is the same. And theta is going to be, in this case, the parameter I want to learn. Okay, so I've got a distribution, well-defined distribution, P of V given H, theta, P of H, and the parameters are theta, this thing. Okay, it may look like a completely bizarre model, but it's a model. Okay. So now we're going to have some data, and in this case I'm going to have one data point alone, so just to keep it simple. So the observation is you get the V is 2.75. And I'm going to assume that I know sigma squared. Okay, it's not fun. So the question is, what is the problem? So the problem is then to maximize the likelihood with respect to theta. Okay, so the likelihood is the probability that you observe V in the state 2.75, given theta, which is the sum over H of P of V given H and theta, passed by pH, summed over H. Is when H is 1, it's e to the minus V, which is 2.75 minus H theta, so it's theta squared over 2 sigma squared. So sigma squared is a half, so 2 sigma squared is 1 over the square root of 2 pi sigma squared. Sigma squared is a half, so it should be multiplied by pH. pH is 1, is a half. Plus the other term for 2H that's the expression for the marginal likelihood. Okay, so you could say, well, that's easy. I can just, it's some complicated function of theta, and I can plot that. But clearly, what's going to happen here is I'm going to have kind of two bumps, right? Another bump around the point here, and a bump around the other point here. Theta. Okay, so theta is around about. So we'll plot this function. So I could certainly, you know, there's a very simple problem, it's a one-dimensional problem. I could just plot this function with respect to theta and find the optimum point. So that's my maximum likelihood theta. However, I'm going to, for the sake of this presentation, I'm going to use the EM algorithm to try to do this as well. Find an algorithm which will do it. Okay. So how would EM work? Well, we need to look at this low bound, okay? So we need to look at this Q's and then the entropy and the energy. So the lower bound is that the log of this observation, the log likelihood, is bigger than the lower bound. So let's say that we first of all choose the Q's to be uniform, right? So let's say, let's just say that we, so what is Q? So Q is some distribution on H, and there are two states. So we have to define the probability of Q is H equals 1 and QH equals 2. But because QH equals 2 is 1 minus QH equals 1, I can just maybe make life a little bit simpler and say, let's just define the probability of QH equals 2. Because then we'll use wherever we see QH equals 2, we'll just use 1 minus QH equals 2. So I could say this lower bound, really then in this particular problem, is just a function of QH equals 2. What is it? It's the entropy plus the energy. This is the entropy, there's a QH equals 1 term, which is 2 term, plus the energy, which is sum over QH of the log of the joint distribution. Okay, the log of the joint distribution is this. I didn't put down the log pi term, I'm afraid, so hopefully you'll forgive me. Plus the log 2, this is from the prior, log p. There's a little constant missing here, which is the square root of pi, but never mind, that's fallen off the edge of the. So that's the, but it doesn't matter, right? The lower, we don't care about this constant because we're going to be maximizing the lower bound. We don't care actually, it's actually absolute value. Okay. So this is your expression, which is QH equals 1 is 1 minus QH equals 2. So now you're going to be, say, somebody gives you the first iteration some QH, and then you'll maximize this vector theta, and you'll do the switching around. Okay, so let's look at the M step. So the M step would be, we would need to maximize the energy term here with respect to theta. So if you assume continuous theta, you now have to maximize this expression here, in other words, minimize this expression here. And that's easy to do because this is just a quadratic in theta. Even though this is sum over 2, I mean, whatever it is, it'll be a theta linear and a quadratic contribution from theta from both terms, which is just a quadratic. So we can do that analytically. We can minimize that expression over theta just with linear algebra. And we'll find actually that the expression is that the theta for the M step, we're saying a new theta is just equal to V times by the average of H of your Q distribution divided by the average, the square of H, which is your current Q distribution. That's just comes from this term. You could figure that out as well. Okay, so that's the N step. So we have to do the E step now. So we need to figure out for fixed theta what is the optimum Q. Okay, so I could go back to here. And I could say, well, I need to, one way to do it would be to say, well, I need to figure out the optimum, QH equals 2. I could, write 1 minus QH equals 2 here, and then I could actually do this explicitly. But we know actually what the answer is. For the optimum one is that QH is proportional to P of H given V at the old value of theta. We know that already, right? So that means I can just jump straight to saying that for the EM, the new theta, or the best Q distribution for H, is just equal to P of H. So your new QH equals 2 is just proportional to the joint distribution, which is PV given H times PH, for base rule divided by PV. Okay, so just plugging in the numbers now, this thing we know, this is this exponential thing, right? PH is just half. So if you just do the normalization, you'll get this expression. Okay, so what I'm using here is this normalization is just, you can figure that out. It's just P of V, it's just sum of P of V given H, PH, sum of H, which is just this. Okay, so that's good, and similarly Q, so Q nu H equals 1, it's going to be 1 minus this expression. And then, so that's it. Now you've got an algorithm for maximizing this low bound, right? So what you could do is you could say start, what do we do here? We start with some, I think I started with some guess of theta here, which is whatever it was, 1 point something. But yeah, about 1.9, something like that. So I started out with a guess for, sorry, I said that before. Started out with a guess for QH equals 2. And then I maximized this with respect to theta, and I got this value for theta here. And then for this value for theta, I maximized over QH equals 2, and I got that value there. And then QH equals 2, I maximized over theta, and I got this value here for theta. You see what's happening? And then I kept iterating. And this what I'm plotting here, this is the lower bound surface. This is the lower bound as a function of theta and QH equals 2. And as you can see, what I'm doing is I'm doing coordinate ascent on this lower bound. Yeah. And on the left, this is actually the log line. This is the log of V of theta. This is the marginal log line. So we see these two bumps as we were expecting to see. So what's happened here is that the theta is then converged onto this value here, which is 1.4 or something, which is this one here. However, if we'd started with a, say, different value of H or theta, we would iterate in the lower bound to this one here, which corresponds to this optimum here, 2.5. So this is not great, right? Depending on where you start, if you decide to start with a Q, initialized line, or theta, depending on how you start, you could get to either a local or a global optimum. You're only guaranteed to get to a local optimum of this. It doesn't guarantee the global optimum. So yeah, we're in trouble, right? And that's the unfortunate situation with latent variables. We don't know. There's no panacea for optimization. We just we're gonna have to try many different things. Okay, does that make sense? Kind of. So what's the advantage? You might say. Well, the advantage is that here you found that this procedure is quite simple, right? It says, well, look, here's an algebraic expression for the optimum theta, or the optimum theta update of the E step. Oh, sorry, the M step. Okay, so it's something I don't have to run, Newton and Raphson or Newton method or conjugate gradient. I've got an expression. Theta mu is this. Similarly, the E step. It's very easy. It just says, Q nu is equal to this given formula. So it's a complete dog. All I do is I start out with something. I start out with some guess of theta, let's say. Then I said, okay, for that guess of theta, this defines QH equals 2. QH equals 1 is 1 minus that. Given this, QH equals 2 and H equals 1. You plug this into here. compute these expectations, still trivial, and you get your new theta. And then you do this again. What could be simpler? So that's nice. So people like this because it's very neat, right? You don't have to run any download some complicated package. But it's it doesn't guarantee we get to the optimum. Not that anything would, but that's one of the. Okay, so now the magic of this algorithm is not just that. It's not just that clearly it's guaranteed to increase this lower bound on the likelihood. That's obvious, right? But actually, the EM algorithm itself is guaranteed to increase, not decrease, the actual likelihood. So at every iteration, it's not just pushing up this lower bound, it's actually pushing up the likelihood itself. And this is less obvious, okay, but it's true. So this is another exam question, so just the motivation again. So how do we show that? Let's look at, say, two consecutive parameter settings for theta. The old one theta and the new one theta prime. So the lower bound in that case is going to be given by the expectation, so the entropy with the Q, which is corresponding to P of the old parameter setting, so it's this, plus the average of the energy term. Okay, so with the new parameters here and the old ones there. And similarly, in general, the log likelihood can be written in the following way. So that lower bound that we found on the log likelihood actually corresponds to the equality of the lower bound is when you have this. So the lower bound is actually, the lower bound is just the difference between the true log likelihood and the KL averages. So in other words, the log likelihood is just given by this plus the KL average. This is just, if you just write this down. So similarly, you can write here, just for notation, you can place this theta prime by theta. So we get the log likelihood is equal to the lower bound with the new theta, the old theta, and this KL average is equal to 0. So that's setting that they're exactly the same. So if you take the difference between these two, so the log likelihood of the new theta minus the log likelihood of the old theta is equal to the log likelihood for the new bound minus the log likelihood of the old bound plus this KL average. So this KL average is greater than 0. So this means that if you choose your theta prime to be such that it has a higher lower bound than your current theta, which is what you would do. The M step says choose a theta which maximizes the energy, okay, which is equivalent to maximizing the lower bound for a given theta. So by construction of, by definition, your M step cannot decrease this term here. It must, you must return a theta prime which has at least as good a value as you currently have for your lower bound. So this is going to be bigger than 0. So this means your log likelihood actually is the likelihood is bigger than 0. So in other words, your new log likelihood or your likelihood is bigger than your old one. Okay? So it's not so dumb. It's quite magical, right? We were thinking we were just pushing up a lower bound. In fact, we're pushing up the likelihood itself. Wow. It's quite nice. This is one of the things that people celebrate about the EMR. Okay, so let's look at a slightly more complicated example. So this is our asbestos smoking cancer example. Now, where we don't observe ever asbestos, but asbestos is in that model. Okay. So we've got this CDNAS, PAPS term, but we never know what asbestos is. It's just missing. And we want to learn these three tables again, but only given this data using maximum likelihood. And we're going to use the EM in this case just for fun. Okay, you don't have to do that, but let's give it a go. So unfortunately, it's going to get a little bit messier with the notation. So we need a Q distribution over the latent variables, right? So in this case, all of the latent variables, they are A, but we've got one per data point. Okay, so we're going to need a Q. I'm going to write N upper index here for the data point, and I'm going to write just a low data point T. This is just going to be the iteration index of the EM algorithm. Okay, so time step number 1, index, iteration 1 of the algorithm. We're going to have some from the EM algorithm, we'd have some, the optimal setting would be that this will be equal to P of A given C, the visible information. C, say, the first data point, S is 1, C is 1. So this one, and given the whatever our initial guess for say theta 0. And we're going to have another one for the second data point. In this case, it's 0, 0, etc. We're going to have 1, 2, 3, 4, 5, 6, 7 Q distributions, given our initial guess for theta 0. So I'm just, I'm writing Q of A. I could write Q of A given B, but I'm just going to get bored of the notation. So this is a shortcut. So what about the M step? So for the EM, Q is easy. It's just P of H given. So the M step, we need to look at this expression. So we need to look at the expectation of log of the joint distribution now. So the joint distribution is P of C given B, P of C given A and S, P of A times by P of S. So take the log of that, and that's going to break out into these three factors: log PC plus log PA plus log PS. And you have to take the expectation of that with respect to Q. Right? So you have to average that with respect to Q, and we're going to sum them up because there are 7 data points in the IID. And each Q is basically going to have Q per data point. Okay, so clearly this term here, this doesn't depend upon A at all, so that expectation is just the same as here. So if you were to do now maximum likelihood, if you were to do optimization of the table for S, actually it is just the same maximizing energy, it's just maximizing the log of the P. So that's easy. This term here though just depends upon A, so we need expectation. This term also depends on A, so we need this expectation here. So your task now will be to find the table P of C given A and S and P of A which maximizes this expression given Q. Okay, this one is easy. This corresponds to maximum likelihood. So P of S equals 1 is 4 sevenths. P of 0 is 3 sevenths. All right. So how do we do this? How do we maximize this expression now with respect to say P of A equals 1? So let's look at this term here. Where does this appear in this energy term? It only occurs here, P of A. If we just concentrate on P of A for the moment, right, then the rest of this, we can just neglect the rest of this term. So we're just going to maximize for the moment this energy with respect to P of A. We'll maximize with respect to P of C given A and S element. Okay. So where does P of A appear? Well, there are two states of A. P of A equals 1, P of A equals 0 in this notation. So the parameter P of A equals 1 occurs here. We're going to have log P of A equals 1 here, multiplied by Q of A equals 1, plus log P equals 0, multiplied by Q equals 0. But if you just use the factor P equals 0 plus P equals 1 is 1, then we could just write this all in terms of, say, P equals 0. So we'd have log P equals 0 times by this term here, the sum over n of those. Okay. This term here is just log 1 minus 8 P of A equals 0 times by the sum of this over n. Okay, so now maximize this expression here with respect to P equals 0, and you get this. The P of A equals 0 is just this ratio here, which is just 1 over n. The sum for n, sum of data price, the sum of the expected empirical expectation that A is at state 0 according to the Q distribution. Okay, so just to go slowly from a bit more slowly, how did I get from here to here? let's call theta equal to log p, sorry, pa equals 0. So pa equals 0 is a parameter. Let's call it theta. Right? So what do we have? We have this thing here says this is log theta. Let's call this thing here some known thing. Let's call it say a. This is like log 1 minus theta. Minus theta. We'll call that thing over there, let's call that b. So you need to maximize this with respect to theta. So what's the usual thing we do? Just we degree we differentiate, right? We try to differentiate with respect to theta. So the derivative of log theta is
1 over theta.
1 over theta. So a plus the derivative of this is 1 over that times by the derivative of that, which is minus 1. And then we set it to 0 for the stationary point. Then you get your algebraic hat on, and you multiply this by theta times by 1 minus theta, so you get 1 minus theta times a minus theta times by b, that's right, 0. So theta, so a plus b, but on the right is equal to a. So theta to a. Okay, so that's all I'm doing to get this expression here. And this one here, this denominator just simplifies simply because we know that probability of being in state A is 1 minus probability of being in state 1. So that just sums to 1. Okay, so you can do the same kind of thing. You say, well, I looked at this expression here, this energy term, and I found the optimum setting for P of A equals 0. Obviously, the optimum setting for P of A equals 1 is 1 minus this. And now I can say, well, similarly, I can figure out what is the best setting of the table P C given A and S by isolating the contribution of that table to this expression here and then maximizing that contribution with respect to the table. It's exactly the same, but it's just a little bit more painful in terms of notation. But what's going to happen is that if you do the same thing, you will end up with the probability for C equals 1, for example, given A equals 0 and S equals 1, one of the settings of the tables, will be equal to some of the data points. Whenever you see C is 1 and S equals 0, you have the factor, the expected probability of A equals 0 according to your Q distribution. And the denominator, you just have kind of a normalization term. But the one way to read this is that this is exactly what you would do in maximum likelihood. Just imagine you had complete data, right? What would you do? You would set this table by counting the number of times that A is in state 0 and S is in state 1. Right? And so say you look through another way to do it is say, I look through the data points when all of these conditions are true. And C is 1, A is 0, and S is 1. I look through all the conditions when C equals 0, A equals 0, and S equals 1. Right? And I just counted the relative number of times that it was 1 C compared to those number of times when I'd selected those total number of times in which this is 1, 0, 1, and when that's 0, that's 0. That's what you would do. This is your maximum likelihood counting thing. I select C equals 1 number of times, C S is 1, and equals 0 divided by this plus this. And all that's happening actually here is that because you don't observe A, what's happening is you're just replacing, instead of having an indicator, a delta function there, just replacing that by a corresponding Q distribution. So in some sense, when you get a bit more familiar with this, and you have to derive the EM algorithm for something, it's actually obvious. You just write down the maximum likelihood update and the M step, and wherever you had a kind of, something which is missing, just replace it with a Q distribution. That's it. You just jump straight to the answer usually. You don't even really have to work it out. Okay. So this kind of, at least for these non-constrained table cases, it's easy. And so with the E step at iteration t, then the Q of n equals 1, QA is just posterior probability, giving you a current or your previous setting of theta. Okay, so we don't, how do you get this? Well, you just use Bayes rule. You've got the network, right? So this means you compute this probability distribution condition upon C is being 1, S is 1, and whatever your current or previous settings for the table is. Okay, so that's it. So the iteration will be, you can start whichever you like. You either initialize Q or theta. But let's say we initialize theta as the class is 0. So this defines our distributions on Q, in which we have to use Bayes' rule from our joint distribution to get these quantities. Given those, we then go back to here and say, well, okay, I'll then set the tables by this expression here to compute this expected thing here, sum over some data points. So it's an easy expression to do, and I do it for p equals 0, and I keep iterating these two, and that will then converge to a local optimum for the maximum likelihood table settings and under the missing data case. So that's it. Basically, that's all there is to it. So the EM is a very simple procedure in principle, but it's got this. It could get trapped like any optimization algorithm in this local optima. Now, where is this? What about this variational thing? Well, I'm not going to say much about it, but the reason is that sometimes it turns out that computing these expectations with respect to the fully optimal Q distribution is painful. Okay, so what you might like to do instead is say, well, actually in variational EM in general, what you could say is, well, yes, I know that the fully optimal setting for Q is to use the P of H could be, but that may be too complex for me. I cannot compute expectations easily with respect to that. So I cannot carry out the E step because I can't compute the expectations required in the E step with that very complicated Q. So what I'll do is I'll restrict the family of Qs just to those families for which I can carry out those expectations. A tractable family. Okay, so you're searching in a sub-family of distributions. And then you could then ask the question, well, that's interesting because we know that you're still pushing up a lower bound on the likelihood. But in that suboptimal case, that you're not using the fully optimal Q, are you guaranteed, nevertheless, to keep increasing the likelihood at each iteration, not just the lower bound? And the answer is that you're not. In general, there's no guarantee that each iteration of this sort of variational EM algorithm, in other words, not using the optimal Q, that is not guaranteed to increase the likelihood itself. It's only guaranteed to increase the lower bound of the likelihood. So at the expense of making a tractable algorithm, you lose the fact that you're pushing up the likelihood. You're guaranteed to push up the likelihood. Okay, so I was going to try to show you some example, but it crashed. Which is not good. But maybe I can show you some notes from another lecture which contains an example. Let's see. So let's look at the Gaussian case. Okay, I'm not going to go through this, the derivation of this, but this is the EM algorithm for a mixture of Gaussians. So what's happening here is we've got a set of data points given by these blue circles. We're going to try to fit a mixture of Gaussians, a bunch. So we're going to try to explain this data So V in this case will be a two-dimensional data point. So V, and the distribution will be. So we're going to have H. So in our plate notation, we have V and okay, so what I'm going to have is I'm going to have this. I'm going to have a mixture. I'm going to have a Gaussian. So it'll be some distribution, say V, two-dimensional V, minus its mean. So let's say the mean of the H index. And let's say I just make them, say, isotropic. D is half here. So. Okay, so this is our this is in general to the power d over 2, but d is 2 here, so I'll just write not to complicate too much. Okay, so what this means is I place a Gaussian, which I think you're all familiar with Gaussian, right? So there's a two-dimensional Gaussian. So if you tell me, so what are the parameters? So we're going to have a h might go from 1 to 10, I think in this case. Going to be 10 Gaussians. Each Gaussian will correspond to a particular mean. And I index these 10 means. So I have 10 two-dimensional means here. So mu1 might be 1, 2, mu2 might be times number 3, 7, and I have 10 of them. And P of h is going to be, h is just an element of 1 to 10. So I'm going to have 10 Gaussians. The parameters are going to be, I want to learn where to place these means. I want to learn the weighting of each of these Gaussians. I'm going to try to explain then data, P of V, as a mixture, as a sum over these Gaussians. So I'll then learn the parameters mu and the mixture weights by En. I'm not going to do the derivation here. We'll do that perhaps in another course, or you'll do it you'll certainly do it in other courses as well. I don't really care about the mathematics of that here. I just want you to get the idea of an En procedure. Okay. And why is this useful? Well, after you've done the training of this, you can cluster data, right? So what's happened is that our data points here now get assigned to some cluster index. So instead of having the original data, we can now explain it in a lower dimensional way. We can say, well, actually, a simpler mechanism for describing the data you have is the following. You could say, well, I will first of all pick which of the Gaussians I want to sample the data point from. So I'll generate that from P of h. Okay, I'll just figure out, I'll sample from the distribution, and I might just say pick Gaussian number 3. Given Gaussian, which might correspond to say this red one here. Given Gaussian number 3, which has got some particular mean, say maybe, then I need to sample a data point from a Gaussian with that mean. So I'm going to sample a Gaussian which is close to its mean, somewhere around there. And that's the way to generate it. So this is nice because it corresponds to clustering. So clustering of data could be viewed in that way. You first of all say, from a generative perspective, which cluster am I going to generate data for first? That corresponds to selecting, generating from here, P of h. Given that cluster, how do I generate data within the cluster? That corresponds to generating from here. So what you do is then you fit a model, a mixture model. To fit in a mixture model, is clustering in a probabilistic sense. So this one interpretation is that it corresponds to fitting a mixture model. So yeah, I want to show you another example. Something called mixture. Don't see it. That's incredible. I've got to be announcing that. Okay, I don't see it, and the demo's not running. So I'll explain it. Okay. Let's imagine that you want to. You've got a supermarket, and you've got products in the supermarket. So you've got, say, this is your customers here, and this is the products. So you have a big matrix. Let's say you have I don't know, 10,000 products in your supermarket, okay. And you've got a store card. So your supermarket is collecting information about which products customers buy, right? So you might say customer 1 bought this one, didn't buy that one. Bought this. Maybe there's some things which are missing. Maybe you just don't know whether or not they bought that for some reason. So you get this very sparse vector of things that they bought. Okay. So you could do this for all of your customers. And you might like to say, well, to figure out, can I cluster my customers in some way? Can I say, well, I've got sort of 10 kinds of customers. Maybe these are, maybe young people tend to buy certain kinds of things, and other kind of, client groups which have various purchasing kind of characteristics. Or what you could do is you could then say, well, I'll fit a mixture model of that. And one simple mixture model to fit would be to say, well, I could have H here, H would be, say, if you want to find 10 product groups, customer types, this H would be 1, 2, to be 10,000. Okay, so if H is customer group number 1, you'll have a probability of actually purchasing product 1. If H is 1, you'll suddenly have a corresponding probability of purchasing product 2. Okay. So what you could do then is you could fit this model to your data, and you will end up then with, when you fitted the model, you can clamp then any particular customer for his given product purchases and figure out the posterior probability of H belonging to one of those 10 customer groups. Okay, so in that way you'll be able to characterize this particular customer as belonging to a particular group. And you'll figure out, you'll be able to sort of tease out product groupings or customer groupings within your product sort of data. And this is used, right? So these kinds of things are used by supermarkets to figure out things about that customer. So if there's missing, one way to do this is this H now corresponds to a latent variable. So we could do by EM, and EM in this case gives a very convenient algorithm. But we could also do other kinds of training as well. Oof. Okay, so that's it, basically for, I'll show you the demo next time. But just to say, for assignments, so there'll be another, hopefully, there'll be another 2 assignments. So I'm hoping to launch assignment 3 this week. So,
one of these. Just one.
Just one? Why?
So much work. We don't have much time. We have, like, I don't know if you talk to you have lectures, but there's a lot of coursework. So, like,
all from the 30th of November or 1st of October.
Okay, but the question is how much work is this coursework compared to the other ones? Is this more or less work than the other ones? More. Okay, it's more, really?
yeah.
Okay.
These are hard.
These are hard, these ones. Okay.
You spend more time thinking about it.
Well, the thing is that there are 2 things about the coursework. One of them, of course, is that you get graded. I don't really care about grades personally. You know, the coursework is there to help you understand the material. That's my interest. So it's not that, if I give you coursework, it's not because I want to burden you with this kind of. I just want to sort of help you understand the material. So one thing we could do is we could have, say, a lighter 3rd assignment, if you like. Maybe a little, not so complicated. And then maybe I said you a 4th one, maybe which you can do over Christmas, which is a little bit more challenging. Yeah. Or maybe another slightly easier, lighter one, but towards the end of the course. That'd be okay. Okay, so I'll set you a fairly generously light one.
Thank you.
Yeah. That's it. I'll see you next time.
Good guy, lecturer.